Okay, so I chose to do my project on computer virus security. And just here's a quick introduction. It's important for users to acknowledge the different types of viruses and the levels of protection that they can get from antivirus software. And furthermore, it is just as important to understand how antivirus software works. And in the following slides, we're going to discuss where viruses come from, learn the types of viruses and how they work, and understand how antivirus software protects users from potential threats. So here is the earliest history that I could find on viruses. If you find that I was wrong, just correct me. So the first virus recorded in history was made in 1971 and was labeled as Creeper. And Creeper was potentially a friendly virus. It copied itself using the ARPANET, which was a precursor to the internet, and displayed the message, "I'm the Creeper, catch me if you can." So, not much of a threat right there, but as you'll find out that viruses kind of evolved into something more dangerous. There's more viruses that I have than listed here, but these were the three ones that stood out to me. So there's the macro virus, the Overwrite virus, and the Trojan. The macro virus is a stealthy virus. It hides in files like DOC and PPS and XLS. And then once the macro is attained, it starts to infect other document files. And typically you acquire these through unknown emails or networks. The Overwrite virus infects itself into files and deletes the previous information. It leaves previous files useless, and it doesn't change the file size. So this makes manual detection more difficult because you don't see that your file has actually changed. It's just rendered useless. And then the Trojan virus is a more common virus. It's disguised as friendly software and can log passwords and usernames. So it makes it really dangerous to log into your online banking or social media. And luckily there's antivirus software to help you stay clear of these viruses. Your computer is constantly bombarded with malware attacks. That is why it is so important to have antivirus software installed on your computer. And most of us know that we need antivirus, but how does it work? Antivirus software comes with a 3-layer protection. You have the on-access scanning, full system scan, and the heuristic scanning. On-access scanning runs in the background. It scans files as you open them and compares files with known virus signatures. And when you have on-access scanning, you typically don't even know it's on because when you open up the files, it doesn't take much of your computer process's power. And when you have virus signatures, that's the basically your antivirus that it knows what viruses you have, and it keeps them logged. So other terms for on-access scanning is resident scanning, real-time protection, and background scanning. And there's other names that your antivirus software might call it. The full system scan scans every file on your computer and compares them to known virus signatures. Because antivirus software comes with on-access scanning, a full system scan may not detect a virus. So if you got a virus on your computer and it passed the on-access scan, a full system scan potentially will not even help. But that's why you have to have it updated, because once you update your software, sometimes new virus signatures will be incorporated, and that way when you do the full system scan, what got through the on-access scan previously will now be detected because you updated it. The heuristic scan is one of the more important scanning features of your antivirus, but it's also has 50-50 chance really of not detecting the correct software, so we'll talk about that real quick. It allows antivirus programs to identify new or modified types of malware, even without virus signature files. It detects shady program executions, so if you had a program on your computer that was potentially a virus, and say it opened up like multiple .exe files, your heuristic scan from your antivirus software will be like, hey, stop, that's dangerous, that's probably a virus, what do you want me to do with it? Which is why it may potentially block safe software. I know I have a problem with this because I like to fiddle around with game development, and whenever I have a new game that I'm working on, a lot of times my antivirus software will pick it up as a threat, and it's not. That's called a false positive. So if you have false positives and you don't know if it's a safe file or not, you can take it to a website called VirusTotal, and it compares potential false positives to other antivirus software. And if the reports say that the file is dangerous, then it's generally safe to say that you should trust your antivirus software. I believe VirusTotal is owned by Google also. So here's some antivirus programs you can download. You can get Bitdefender, GData, Kaspersky, Bullguard, Avast, AVG, McAfee. There's a lot of other ones, and you can test them out with the EICAR test, which is a universal test that can be downloaded from the organization at this website. And you can just find out what virus software you want and see how well it puts up. So the test is basically a fake virus, and if it's not going to hurt your computer, but it's a good way to test out your software. And yeah, that's it. Really short. Sure.
What's the software, antivirus software you use, and why do you recommend that?
I use Bitdefender because from my personal experience, it's picked up a lot of issues, and then also it's not really that taxing on your computer, and it hides in the corner. It doesn't pop up in your face. It's not really like adware, so it's just real nice to have. And I got it for free.
Is it free?
You can download the free version, or you can update into the web security and stuff. But
So Bitdefender?
yeah, Bitdefender. Yep.
Okay, let's give him a hand. Good job. So I'll have you put this on as well, and just a little button here you press. So I'll click on the back. Make sure. Pick up. It's all ready to go.
Test.
Just put it on your shirt or whatever. That'd be awesome.
Yeah, just moving ahead, just use the enter key or.
Yep, I'll show you. You want to use, this big space bar key if you're just going to go forward. If you do need
But
to
I
go
mean,
back,
yeah.
you can use this back arrow key.
Okay.
Okay?
All right. Thank you.
All right. It's all yours, sir.
Okay.
Let's give more attention.
Okay, my talk's going to be on digital certificates. But to get to that point, I have to take a few minutes to explain general computer security, a little history. Besides what Jonathan spoke about, antivirus software, there are firewalls, which are your first line of defense, and there are software programs that are a defense between the internet and your local network, intranet. And then there's what they call the Java sandbox, which is a layer of software called a Java virtual machine, and that prevents downloaded programs from gaining access to the computer's hard drive. And then what I'm going to talk about today is the digital certificates. Definition: digital certificates is a technology used to associate a user's identity to a public key that has been digitally signed by a widely trusted third party, which they call a certification authority. We know it like VeriSign is, or CyberTrust are private companies that are trusted third parties. And it's a method widely used on the internet to keep communications secure. And the purpose is to confirm that a particular public key belongs to a particular person or entity, ensure that conversations and transactions remain confidential. Um, just a little history. It involves coding, and the history of code goes back 2,000 years to Caesar. Most of the time it was used 95% of the time in military strategies to communicate, and governments communicate between each other. And it was all done with ciphers. We all know, like cryptocode, substitution ciphers and transposition ciphers. And no matter how complex code has got, with the advent of computer technology and digital, those are the basic methods that are still used. The weak link is the key. If you know the key of if you know a cipher is a transposition every third letter, or a exchange between a 0 and a 1 in the ASCII code, you'll know how to translate it immediately. If you don't have the key, you can't. With the codes that have been developed since World War II, with the Enigma, the German Enigma, and that, it would take you large computers and resources only governments had to decipher in a reasonable amount of time. But with the advent of modern computer technology and IBM, they had a guy who was a German, but he was interesting, kind of a character who developed Lucifer, which was the first coding system. Lucifer, it was called, by IBM. And NASA, of course, didn't want this to happen, but IBM, because of the e-commerce and their power, allowed them to have this Lucifer code, which was pretty much unbreakable, even to NASA, NSA. I say call it NASA, but NSA. And with that came private organizations like banks, for instance, still had to move their keys under lock and key in a courier. And it was a very difficult thing to do. You had to have a vetted employee that could travel and carry that key, key meaning the formula to unlock the code, to decode. It just became impossible to do these things, to move keys manually. And that's the only really safe way to move a key from between parties. And then in the 1970s, middle 70s, two guys called Whitfield Diffie and Martin Hellman, who were just garage guy mechanics like Steve Jobs. They came up with public key cryptography, which meant they eliminated the need for a key. You didn't have to move the key in order to keep your code secure. With that, they developed, which we had read, DES was developed, and that was a cipher or a key that had a number. It was a one. They call asymmetric math, where the formulas only go one way. It's like a clock. You can go forward, but you can't go backwards. And so the keys were really hard to break, and they were also very affordable, and they could write programs to disseminate them amongst the general population. And so the codes became very good. The problem became, with all the different entities, was the standardization. You needed a standard coding system, or a code that everyone was going to use. And that's where DES came to be. Data Encryption Standard came to be. And that was, not going into the math, but it was like the key was a number that was like 1 times 10 to the 23rd in length, in digital length. And it was so large that they called it a 56-bit, because in 56 bits you can get this really large number, a 56-bit key. And then that was broken in the 80s, and then they came up, and then the AES was developed, which I think is still in use today. But even with this aspect of it, you still need a third-party verification. So, these trust model types, I'm going to go by that pretty quickly, because the management and distribution of digital certificates is, it's a whole another area, but it is well managed. And let's let's see. I'll talk about the basic encryption techniques. The first was the symmetric key, where both sender and receiver had the same key. And then asymmetric was the public key cryptography, which was the Diffie-Hellman. And the balance has always been between privacy and key recovery. Weakening security with the aim of strengthening security does not make any sense. Good fences make good neighbors type of thing. When you have good security, you have trust. And then trust builds confidence. And this is basically, I broke down a diagram here. There's going to be 3 modules. In the first module, I use the conventional Alice and Bob. Let's see here, Alice. Okay. I'm going to have to read my notes here. See. When I put this out, I thought the notes were going to come up, but so it would start with Alice on the left, and she uses her cryptographic software to generate a private key, which is the purple one, and a public key, the gold one. She sends the public key to a certification authority and asks for a digital certificate. And the authority there is the government-looking building. The authority needs to authenticate Alice's identity. This may involve verifying private key information that Alice supplies. The authority issues a digital certificate, and they just use the CA there on the ribbon for certification authority, affirming that the public key does belong to Alice. Attached to the certificate is the authority's digital signature, which can be verified by anyone who knows the authority's public key. And then the number 2 there, the certification authority's public key is distributed to anyone who needs it. And that would be, Bob will eventually need that. He doesn't need it, but he can always check it, and he can actually open a message with it. The authority issues a digital certificate, and then the key is typically embedded in web browsers for secure computer communications. Didn't look into that too much, but Chuck, is that like it's in Explorer and Chrome? And okay, and then that was basically there. The public and private key asymmetric. The public key, the gold, goes to the authority. They certify it. Alice has a picture ID or something. I don't know how they do it, but they do certify that they validate it as the person that they say they are. They send that certified key back, and now she has still the private key, which that's the password, nobody knows but her. And then Alice, in her communication with Bob, she sends, go to that one here, my notes. She digitally signs her message to Bob. First, she applies a mathematical formula called a hash function in the message. This formula creates a message digest, which Alice encrypts with her private key to make the digital signature. And that's E there with a little stamp there with Alice's text there, the printing, at about 7 o'clock. When she sends the signature to Bob along with the message, and the message there is, you can't read it with this, but it's like a hieroglyphic code. The hash, they call it, the hash. Everything's mixed together. She also attaches her digital certificate, which includes her public key, which is there at about 2 o'clock. And so that goes to Bob. Okay, then from Bob's point of view, Bob uses the certification authority's public key to verify the authority's digital signature on the certificate. Bob can now be sure that the certificate is authentic and that public key of the certificate belongs to Alice. Bob then uses the key to decrypt Alice's digital signature, which recreates the message digest. Finally, Bob applies the hash function to Alice's message. If the message digest produced this way is equal to the message digest decrypted from Alice's digital signature, Bob can be certain that the message is indeed from Alice and that it has not been tampered with by anyone else in the network. And that's just an overview of what occurs. So the third party there. And that's basically it. I was going to talk a little bit about this balance. Even though Ed Snowden's in the news a lot, this Zimmerman, who developed pretty good privacy, has actually made a much bigger dent on computer security in the world. And he was actually, even though it wasn't headlines, he was charged by eventually he was harassed for a while, and then he wrote this program. And then the government was, should we charge him, shouldn't we? And then they decided not. They went through years. I don't know if he probably had excellent legal help because he had a crowdfunding way back in the 80s to help him with his legal costs. But they decided that he didn't break any law. The law they thought was this exporting arms. There was a law against exporting any type of thing that could be used against the U.S. But he never sold any of the program to anybody overseas. There was a text sent, but somebody, a friend or associate, did have it on their computer, so he was one removed. So the technicalities were too much for the FBI to even. They thought this is just going to be, we're going to lose more here than we're going to gain, and we're going to look bad and blah blah blah. And so it developed that PGP became a commercial product, and I think he had a happy ending. I think he got in a company that produced it, and of course we had our exercise in the lab on PGP. So the good part is that security is secure. Internet security is good. The big Apples and Amazons and Googles want to keep it this way. Government folks want to have the backdoor key. They want to be able to get into any decrypted, especially now with all the political stuff going on. But it looks like it's going to stay the same the way things are now. So.
One of the larger digital certificate authorities you mentioned?
VeriSign? That's the one I use because they always have that little key. They have that little trademark brand that everybody kind of knows. But
Yep.
and I think.
Good job.
Yeah. Thank you.
Yeah,